Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at polyprotic titrations as we finish up acid-base chemistry. So one of the big features to remember about polyprotic titrations is that we aren't going to have just one equivalence point. We can have many. And one of the things that's worth noting is in practice, you may need a different indicator for every single equivalence point to help make sure you've arrived at each individual point. So let's go ahead and take a look at what do we really mean when we're talking about polyprotic titrations. And it turns out that we don't just have titrations for monoprotic systems like acetic acid. You often have a lot of polyprotic systems, especially in biology, which you can try and identify by doing polyprotic titrations, where you can identify how many pKa's are present and where they are. And this is a very good way of trying to identify different types of amino acids that might be present in a system, as well as any number of other biological molecules, such as nucleic acids, that are, as the name indicates, acid-base active. And so traditionally, you're going to perform one of these titrations by acidifying your system and then adding a strong base such as sodium hydroxide to your fully protonated species. And it is worth noting that what we're really doing here is a much more nuanced version and a longer version of a weak acid strong base titration. And like any of our other titrations, the first step is going to use an ice table to try and determine where we are in the system and which of our acids and or bases are going to dominate the system. So keeping in mind those alpha tables can be really helpful in trying to assign where we are along the titration. So it's worth noting for our monoprotic systems, we only had 6 parts of our titration curve. So for a diprotic system like glycine, we've now expanded that into 6 individual parts. And it is worth noting that because we have so many different parts, I'm going to, and glycine is fairly big, I'm going to annotate each of our protonated states based on the charge and the number of protons present just for convenience. So the first part of any titration is going to be before I add any of my sodium hydroxide. So in this case, all we're going to have is our fully protonated weak acid system. As we start adding in sodium hydroxide, we will have partially converted some of that acid into its conjugate base, that monoprotic version. And we're going to have a buffer region centered on our first pKa. As we add a full equivalent of base, we will have fully turned all of our doubly protonated H2 acid into the amphiprotic HA species. So we're going to have to use our amphiprotic conditions to determine the pH. At this point, we get into the fun part because now we're starting to convert that amphiprotic HA into its conjugate base, in this case, A. So our fully deprotonated glycine. And it's going to also generate a buffer region centered on pKa2 now, as this is now the reaction that's taking place, this removal of the second proton with its own associated pKa. After 2 full equivalents of sodium hydroxide have been added, I will not only converted all of H2A to HA, I will have then converted HA to A. And so the only acid base present is going to be A-, which will just be a simple weak base system. From here, any excess sodium hydroxide will then control the pH, and we're essentially just using strong base calculations with paying special attention to the total amount of volume added, which at this point can be quite substantial. So this is the overarching theme of where these calculations will be driving us. Let's go ahead and dig into what this looks like mathematically. And so let's go ahead and look at the titration of 1 molar of the fully protonated glycine with 1 molar sodium hydroxide. So if I've got 20 mils of my glycine, let's go ahead and try and determine the pH before any sodium hydroxide is added. So at this point, the only thing present is going to be a weak acid with a pKa of 2.35. So we can then convert this to a Ka of about 5 times 10 to the negative third. And so this will just be like any other weak acid problem because we only care about the loss of that first proton. So my initial concentration is going to be 1 molar, and we're going to assume no initial amounts of either our conjugate base or the free proton. So we'll end up producing more of those protons. And so this should look fairly familiar. We can then plug in these equilibrium values into our equilibrium constant and then try and solve for x. And in this point, we can probably assume that x is fairly small. And it turns out in this case, the approximation is okay. We have about a 6% decomposition of our weak acid, which again isn't too surprising. pKa1 is fairly low, and it isn't too surprising for the approximations to start to fail with pKa somewhere between about 2 and 3. However, it is worth noting that it's only barely affects our sig fig, so we can go ahead and try and assume that this will be the that this works fairly well. And using this proton concentration, we can then solve for the pH using the negative log. And it turns out that this pH will be about 1.2. So yes, the system is actually fairly acidic. So this means that if I have fully protonated amino acid, because most of the amino acids have a very similar pKa1, they will generate fairly strongly acidic systems. Now let's go ahead and see what happens when I add in 10 milliliters of the sodium hydroxide. So the first thing we're going to want to do is figure out how many moles of my acid is this and how many moles of my base. So it turns out that this is going to be about 20 millimoles of our conjugate of our fully protonated glycine and about 10 millimoles of hydroxide. So you may notice here that this is going to be a very special point on our titration curve. We've added 1/2 of an equivalence. So we should be at the halfway point, and let's verify with our ICE table. So we should go ahead and be able to plug in our 20 millimoles and 10 millimoles of our acid and base respectively, remembering that this reaction should go to completion so that one of these two reactants should go to 0. I have less of my hydroxide, so our hydroxide should go to 0 and X should be 10 millimoles, meaning that we'll have converted half of the acid into its conjugate amphiprotic base. So we've got equal amounts of HA and H2A. So since I've got both these species present, it means, ta-da, we're going to be using our first pKa. So it's Henderson-Hasselbalch time. So using our first pKa value and substituting moles for molarity, which we can get by with in this case because it is indeed, they both occupy that same 30 milliliters of volume. So in this case, we're in the special case of a 1-to-1 ratio, which means that our pH should be equal to the pKa. So at this point, we are in the middle of the buffer region with a pH of 2.35. And again, if I add a little bit more base, it should be a little higher, a little bit less base, it will be a little bit lower. Now, what will happen if I up the amount of sodium hydroxide to 20 mils? So let's go ahead and again, find the amounts of our acid and strong base in this case, and it'll be 20 millimoles of each. Plugging this into our ICE table, you'll note that we're at, again, a very fun point. We have equal amounts of both the acid and the base. So since I'm consuming both, we should have both of them go to 0, converting all of my H2A into the amphiprotic HA species. So we have reached our first equivalence point as we fully converted H2A to HA. So at this point, we need to ask ourselves, what type of reaction do I have? Well, it turns out HA is amphiprotic. It can gain a proton or lose a proton, which means the pH tends to be smack dab in the middle of our two pKa's. So we'll take the average of our two pKa values, and it turns out we have a pH of about 6.1. So again, by adding that first equivalent of base, we've raised our pH fairly significantly. Now let's go ahead and see what happens if we add another 10 milliliters of sodium hydroxide. So at this point, things start getting a little fun, as we've now added 20 millimoles of our acid and 30 millimoles of our hydroxide. So what we're going to find here is that we now have more hydroxide than we have H2A. So we will completely consume our initial acid concentration. As we see here, with less moles of H2A, as I consume it, we'll generate 0 moles of H2A, and we'll have 10 millimoles of hydroxide left, having generated 20 millimoles of HA. So at this point, it's very important you ask yourself, what do I have? What type of problem have I obtained? In this case, I have a strong base. A strong base will always react completely with any acid present. And so what acids do we have? Well, we've completely consumed our original acid, but we do have this amphiprotic HA, which it turns out hydroxide can actually react with the remaining monoprotic HA, so our neutral glycine, to form the fully deprotonated glycine. So then the question is, now who's limiting? And in this case, we're going to find as we consume both our monoprotic and our strong base, we'll now have, we should now have 0 millimoles of our hydroxide left and 10 millimoles of our HA, producing 10 millimoles of our conjugate base. So from here, the pH can be determined using Henderson-Hasselbalch and now pKa2, where we've got 10 millimoles of each. So again, equal amounts of both acid and conjugate base should generate a pH equal to the second pKa, again, just short of 10. So now let's go ahead and see what happens if we add yet 10 more hydroxide, as we now add 40 mils of sodium hydroxide. So this is going to correspond to about 20 millimoles of our original acid and 40 millimoles of strong base. So this will get a little bit fun. Because yes, indeed, again, we will completely react all of our original acid, now leaving 20 millimoles of our hydroxide and 20 millimoles of our conjugate amphiprotic base. However, because it's amphiprotic, it can yet lose another proton. So now we've got 20 millimoles of HA and hydroxide, meaning the reaction should consume both equally, sending both our monoprotic and strong base concentrations to 0, leaving behind just 20 millimoles of A. Well, this means that I've essentially added 2 equivalents of hydroxide. So for every 1 millimole of my original acid, I have 2 millimoles of hydroxide. This means that we've fully deprotonated the system twice, which again, indeed, we observe. So all I'm left with is a system of just the conjugate base. So this means that we now have a weak base system, because this is our only acid-base species remaining. So in order to determine the pH of a weak base, we need to first determine the concentration of said weak base, which is about 0.33 molar, again, using the feature that millimoles divided by milliliters is the same thing as moles per liter. Then we also need to watch out for the fact that since it's a weak base, I no longer need my pKa's, I need my pKb's. So we can get the first pKb using the second pKa, which should give a value of about 4.22. So under these conditions, what we're going to find is that we're going to have an equilibrium in between our fully deprotonated glycine and our amphiprotic neutral state glycine with a pKb of 4.22. And we can go ahead and again treat this with an ice table. We have an initial concentration of 0.33, and I can use molarity because now my volume is no longer changing. Then we're going to be consuming our conjugate base to produce a little bit of excess hydroxide. The question is how much? And from here, we can assume that X is fairly small to go ahead and try and solve for the amount of hydroxide present. So for here, we're going to use our first equilibrium constant, Kb1, and then set that equal to the ratio of products over reactants. So again, solving for X, which will be our hydroxide concentration, this will be the square root of our initial concentration of base times our Kb of 6 times 10 to the negative 5th, which gives us a hydroxide concentration of about 4.5 times 10 to the negative 3rd molar, which is indeed significantly less than our original 0.33 molar base concentration. So this approximation just barely holds. However, now that we have our hydroxide concentration, we can then go ahead and calculate for POH, which should be about 2.35, and then use that to solve for pH of about 11.6. So again, the system is now fairly basic. So after having gone to two equivalents, we end up with a fairly basic weak base system. However, wait, there's more. What happens if I add another 10 milliliters of sodium hydroxide? So in this case, we can see what happens when we have got 20 millimoles of H2A and 50 millimoles of hydroxide. So again, using our ice table, we find that we have more than an excess of the hydroxide. So we'll have about 30 millimoles of hydroxide left, which will readily react with the remaining 20 millimoles. Again, completely react, leaving 10 millimoles of hydroxide behind after having fully converted our 20 millimoles of H2A into the fully deprotonated A. Whew, that's a lot. So then we have to ask, what do we have? We have a strong base. We have 10 millimoles of it, which is quite a lot. Is there any acid for it to react? Nope, consume that. Consume that, no more protons to pull. So yep, we've got a strong base problem. So our pH will be dominated by that excess hydroxide, which is going to have a concentration of, again, 10 millimoles over a full volume of 70 milliliters so far, which will give a molarity of about 0.14, which we can convert to POH of about 0.9. So yeah, that's pretty basic because that's a pH of about 13. And again, the pH will slowly converge to the pH of that 1 molar sodium hydroxide, which has a pH of 14 as we add more sodium hydroxide, because we can never get a pH higher than the 14 that we're adding. So there's a lot of moving parts to these polyprotic systems. And so one of the very useful features is trying to break them into the key regions to figure out where you are in the titration curve. So if you're essentially at or near one of those halfway points, you're going to be treated as a buffer, and the pH will be fairly near the pKa. And if you're trying to figure out how many buffer regions a molecule have, it will have as many buffer regions as it has pKa's. So glycine has 2 different pKa's, 1 and 2, so it has 2 different buffer regions, so flat-ish regions on the titration curve near those separate values. In between these buffer regions, you reach these equivalence points. So these equivalence points are usually either dictated by an amphiprotic species, like our neutral glycine, or by a weak acid or base at the end of a titration, with, again, a level off, the pH eventually leveling off to the pH of the titrant. So if you have a 1 molar sodium hydroxide, it will end up approaching a pH of 0 or 14. If you have a 1 molar HCl, it will approach 0. If you have 0.1 molar sodium hydroxide, it will approach 13. So one of the big parts with polyprotic systems is there are a lot of moving parts, but try and focus in on figuring out where you're at. And if you don't know, break it down into a series of ice tables to help you out. Next time, we'll slowly move on to solubility as we leave acid and base behind for now. Until then, take care.